All right, first I would like to thank the organizers for giving me an opportunity to give a talk in this conference. This is a joint work with Godad, Shivaji and Son. First, I want to talk about the modeling aspect of our problem. Basically, we have a habitat, omega star, in which a certain population is living, which is surrounded by a hostile region, which is what we call the matrix. In this model, D is the diffusion rate, R is the intrinsic growth rate of the patch. Patch is our domain. And this alpha tilde of V is the probability of the population staying inside the domain upon reaching the boundary. And this composite parameter is a parameter related to the hostility of the matrix. And these components are defined as follows. And 1 minus alpha tilde of V is what we call the dispersal, or the probability of the population leaving the patch. And of course, here is the initial distribution. And this equation describes the population density of the species living in this habitat. Okay. All right. The first thing that I want to do here is I'm going to rewrite my original domain omega star. We are a scaling of a fixed domain whose measure is 1 and which has the same geometry as the geometry of the original domain. And if you do this domain scaling, we are going to come up with this particular model with L being the patch size of your domain, size of your original domain. To make this model look simpler, I'm going to use this substitution. Lambda is equal to this quantity and gamma is equal to this quantity. And we come up with this model. Okay. In this model, lambda is a parameter related to the patch size, and gamma is a parameter related to the hostility of the outside region. Again, this alpha of U is the probability of the population staying inside the domain upon reaching the boundary. And if someone is interested in knowing the details of the derivation of this model, here is a paper where you can find all those derivations. This is a paper by Cronin, Godad, and Shivaji. All right, so I want to give a motivation before I introduce my model today. In 2019, we studied this general model with f of u being a logistic reaction term. What I mean by a logistic reaction term is that your per capita growth is decreasing linear function like this. And we took our alpha of u to be this particular function with a and epsilon are two positive parameters. In that case, your 1 minus alpha u, that is the dispersal, is going to be u-shaped like this. Okay, so this is a logistic growth model with u-shaped density dependent dispersal on the boundary. For this model, we proved several interesting results, and here is one result that we proved for that model. We showed that there exist at least two positive solutions to the left of E1 gamma comma a squared plus epsilon for a certain range of lambda, and no positive solutions for lambda small. Okay, so here are two scenarios that we could expect. Actually, in the one-dimensional setting, we observe that both of these bifurcation diagrams occur. And here, this E1 gamma comma a squared plus epsilon is understood via this definition. We define E1 gamma comma d to be the principal eigenvalue of this particular eigenvalue problem. Of course, this is the linearized eigenvalue problem associated to our model. And the existence of the principal eigenvalue for this problem follows from this paper by Godad, Morris, Robinson, and Shivaji. All right, here is the model that I want to focus on today. I'm going to take the same alpha u that we took in the previous model. That means we have the same u-shaped density dependent dispersal on the boundary. And this time I have a weak Cayley growth reaction term. Okay, so what I mean by a weak Cayley growth reaction term is that your per capita growth rate is initially increasing and then decreasing. Okay, to make the notation easier, I'm going to take this green piece to be f of u. That's my reaction term. So this is the model I'm interested in today. So I will call that number 2. All right, for this model, we proved several non-existence, existence, and multiplicity results. Before I go into my results, I want to introduce something called property A. In defining property A, I use this abbreviation. I take E1 tilde to be E1 gamma comma A squared plus epsilon. My property A means basically this bifurcation diagram. Property A means there exist two positive solutions to the left of E1 tilde for a certain range of lambda, no positive solution for lambda small, and there is at least one positive solution for lambda bigger than E1 tilde, such that the subnorm of that solution goes to 1 as lambda goes to infinity. So that's what I mean by my property A. All right, having introduced property A, now I'm going to state two theorems that we proved in our study. If you take any A between 0 and 1, epsilon greater than 0 and gamma greater than 0, then the solution set of our model has property A. Basically, we can show that we can establish this bifurcation diagram for our model. All right, next theorem 2. If you take any lambda tilde bigger than A1, then there exists gamma star. And for gamma greater than gamma star, there exists epsilon star, such that our model has at least 3 positive solutions for lambda between E1 tilde and lambda tilde when your epsilon is less than epsilon star. Okay, here this A1 is the principal eigenvalue of the negative Laplacian with Dirichlet boundary conditions. And what this theorem 2 tells you is that if you choose your gamma big enough and epsilon small enough, you are going to have at least 3 positive solutions to the right of E1 tilde for a certain range of lambda. That's what it simply tells you. Of course, this range in which you get 3 solutions, you can make that range as big as you want by choosing gamma big and epsilon small. All right, I want to give you a rough sketch of the proof of theorem 1 today. So for that, I'm going to use the method of sub and super solutions. So let me first introduce the definitions of sub and super solutions. Any function psi satisfying these two inequalities is called a subsolution. And of course, if one of these inequalities are strict, it's a strict subsolution. And any function z satisfying these two inequalities is called a super solution. And a strict super solution is understood in the same way. All right, so this is the first lemma that I'll be using in establishing my results. If you have a subsolution psi and a super solution z such that your super solution is bigger than or equal to the subsolution, then the conclusion is that you have a positive solution in between your sub and super solutions. And here is the next lemma that I want to introduce. If you have a small subsolution psi1 and a bigger super solution c1, and in between those two sub and super solutions, you have another strict subsolution psi2 and a strict super solution C2, such that your strict subsolution is bigger than the strict super solution in at least at one point in the domain, then there exists a solution U1 in this ordered interval and U2 in this particular ordered interval. Of course, the existence of these two solutions come from the previous lemma. And there exists a third solution in this particular interval, and which can be shown using degree theory. All right, now I'm going to give you a proof of a sketch of the proof of theorem 1. Here is my model again. Here is my theorem 1 again. Basically, we have this bifurcation diagram. Okay, we can establish this bifurcation diagram for my theorem, for my model here. All right, first I want to show that there exist two positive solutions to the left of the bifurcation point. For that, I'm going to establish this diagram to apply my lemma 2. Okay, so as you can see, if I take psi1 to be 0, it is going to be a sub-solution because it's a solution to our model. And clearly z1 is equal to 1 is going to be a global super solution for my problem. And now I'm going to construct a strict sub-solution in between those two sub and super solutions. Okay. To construct my strict subsolution psi2, by the way, I'm constructing that subsolution for lambda less than E1 tilde. To construct that subsolution for a fixed lambda, I'm going to take sigma lambda to be the principal eigen value of this problem. And here are two interesting results that we can prove. Okay, so if sigma lambda, if your lambda is less than E1 tilde, your sigma lambda is positive. and your sigma lambda goes to 0 as lambda approaches to E1 tilde. So these are two interesting properties that you can prove, and the proof can be found in this paper by Goddard, Morris, Robinson, and Shivaji. All right, for my sub-solution, I'm going to take psi2 to be delta lambda, delta lambda. Delta lambda is defined this way. Here, this A star is a positive quantity such that if double prime S is bigger than A star for a small s. Such a quantity exists by our reaction term. Okay. All right, now if I compute this difference, negative Laplacian of psi2, that is going to be equal to this expression because of this eigenvalue problem. By the way, this theta lambda is the eigenfunction associated to this eigenvalue problem. So this negative Laplacian C2 is going to be equal to this expression, and lambda times f of psi2, I'm going to replace this quantity by this expression by Taylor's theorem. Okay, and notice that if you choose your lambda close to E1 tilde, this delta lambda is going to be very small number because sigma lambda approaches to 0 as lambda goes to E1 tilde. So that means your psi2 is going to be small if you choose your lambda close to E1 tilde. So that means we can apply the Taylor's theorem when lambda is close to E1 tilde. And now we can replace this f double prime eta by A star. By the way, this eta is a number between 0 and psi2. Now, if you replace this by A star, you get a bigger quantity because f double prime of S is bigger than A star for S is small. Okay, but by the choice of delta lambda, this quantity is 0. Okay, so we have this inequality in the right direction for psi2 to be a strict subsolution. The first part is okay. Now the boundary term, if you compute this term, and from this again from this eigenvalue problem, this psi2 over d eta is going to be equal to this expression. And as you can see, if this psi2 is small, then a square is going to dominate this term. So that means this whole quantity has to be negative if psi2 is small. But in fact, psi2 is small if you choose your lambda close to E1 tilde, because your delta is going to be small if you choose your lambda close to E1 tilde. All right, that tells you that psi2 is a strict subsolution for lambda less than E1 tilde and lambda close to E1 tilde. What that means is that psi2 is a strict subsolution for lambda between lambda bar and E1 tilde for some lambda bar greater than 0. Okay, so I have my strict subsolution. Now I'm going to construct a strict super solution. Okay, so to construct a strict super solution for a fixed lambda greater than 0, I'm going to take mu lambda to be the principal eigenvalue of this particular eigenvalue problem. Here, one interesting property that we can prove is that mu lambda is greater than 0 when lambda is less than E1 tilde. Okay, the proof of this property can be found in this particular paper. This is a paper by Goddard, Morris, Payne, and Shivaji. Now I'm going to take Z2 to be this function beta times phi lambda. Phi lambda is the eigenfunction associated to this eigenvalue problem. Now, if I define this function h of s this way, you can easily notice that h of 0 is equal to 0, h prime of 0 is equal to mu lambda, which is bigger than 0 because I assume that my lambda is less than E1 tilde. Now, if you compute this difference, negative Laplacian C2 minus lambda f of C2, it is going to equal to this one. Now, if your Z2 is small, this is going to be positive because of these two properties. If you look at this function back, if your S is small, this quantity is going to be positive because your h of 0 is 0 and h prime of 0 is mu lambda, which is positive. Okay, so the derivative is positive at 0. So this is going to be positive if C2 is small. In fact, your C2 is small if you choose your beta small. Okay, so for beta small, we have this inequality. And if you go to the boundary inequality, we can compute this dC2 over d eta using the boundary conditions of this eigenvalue problem. And if you simplify this, here is what you are going to get. In this expression, if this C2 is small, this expression, this one is going to be close to 0. Okay, So that means this whole thing is going to be positive because your mu lambda is positive. So we have the two inequalities in the right direction. So that means C2 is going to be a strict super solution for lambda less than E1 tilde if your beta is small, if you choose your beta to be small. So that means we have a strict sub-solution and a strict super solution. Of course, you can choose your beta further small so that your strict super solution is less than your strict sub-solution in at least at one point in the domain. So that means by lemma 2, our model has at least two positive solutions for lambda between lambda bar and E1 tilde. So that establishes two solutions, existence of two solutions to the left of the bifurcation point. Now to get the existence for lambda bigger than E1 tilde, I'm going to try psi to be beta times phi lambda. Phi lambda is the same eigenfunction that I used in the previous part. Now using the fact that mu lambda is less than when lambda is bigger than E1 tilde, we can show that this is going to be a sub-solution this time if you choose your beta small enough. And also notice that C1 is equal to 1 is a super solution, global super solution. So that means we have a solution between this sub-solution and the super solution. So we have the existence for lambda bigger than E1 tilde. All right, now to show that there exists a positive solution u lambda such that the subnorm of u lambda goes to 1 as lambda goes to infinity, I'm going to look at this particular boundary value problem. This problem was studied by Shi and Shivaji. They proved that this problem has a positive solution w lambda such that the subnorm of that solution goes to 1 as lambda goes to infinity. Now I'm going to take psi to be w lambda, and then using the Hopf maximum principle, we can easily see that this psi is going to be a sub-solution, a strict sub-solution for our model, okay? But again, C1 is equal to 1 is a super solution. That means there has to be a solution between W lambda and C1 for our model. What that tells you is that the subnorm of that solution should go to 1 as lambda goes to infinity, because the subnorm of W lambda goes to 1 as lambda goes to infinity. So that establishes that result. So basically we have established this bifurcation diagram except for the non-existence for lambda small. Of course, the non-existence for lambda small is obtained using the Green's second identity, and it easily follows. I'm going to omit the proof. So with that, we have this complete bifurcation diagram recovered. All right. Next, here are some references that I was using in my talk. In particular, in this paper, you can find all those modeling aspects of our model. All right, thank you for your attention.